introduction. I'm a geographer, a geomorphologist, working especially in geomorphometry, so the quantitative analysis of Earth's surface, which is nowadays made mainly on DEMs. So while extracting landslides from high-resolution digital elevation models based on LiDAR technology, I also saw hill forts and tumuli, which I used in conjunctions with landslides, which affect or precede this type of features to relatively date landslides. And after I did my geomorphological stuff, I said, okay, let's see what can I do also with the tumuli, with the burial mounds. My approach, you will see, I don't know, it's a little bit different from what was presented before. The idea is to delineate them, to actually identify them first and possibly delineate them in order to be known, in order to be included in catalogs, for the national authorities, because you will see compared to, for example, the paper from Hungary, we still have burial mounds which have topography. But of course, tillage in time will basically remove the topography. The ones that are on tillage land, they are smoothed. The ones that are on pastures, you will see they are quite interesting. And in Romania, especially north-eastern Romania, they do not have that surrounding ridge. But they have a concave feature, which is due to tillage, because when they approach them, then they cannot go over the burial mound, they surround it. So the idea is to create an inventory in a, I would say, automatical way, but it's we will discuss that it's quite difficult. In northeastern Romania, the majority of tumuli are from the Bronze Age period, but there are also later burials in those tumuli. They are dated, they are investigated, but there are too many to be all of them investigated. It's very easy for Yamnaya burial mounds because when they find the skeletons, they see the ochre, the red ochre inside. So this is an example of a big one, which is on a pasture land, on a ridge. It's very well preserved, so you can see the features, but not all of them are very well preserved. Since I have background in geomorphometry, we could approach these types of features in a mathematical way, but they should be perfect. If they should be conical, perfectly conical, you could approach them in a mathematical way with an index of shape. But actually, because you have different, let's say, modifications of the initial shape, it's very difficult to do it in a mathematical way. That's why usually you do it in a statistical way. You select a certain data set, you delineate them, and you use DEMs as images or as values, and you use a statistical model to train and identify them. In the beginning, I basically used the random forest algorithm. It's a paper that it's already published. I did a review in the literature, and at that point, let's say 5 years ago, the pixel approach was used. So the idea was to identify pixels which are located on burial mounds and classify them as burial or not burial. In my approach, I proposed an object-based method. So first, we identify segments over the surface, and then we classify the segments. And in this way, you better identify and delineate them. And my view is that basically, when you have pixels, you have many false positives or false negatives that you need to check. When you have polygons, it's easier, even if it is not perfectly accurate, to eliminate those that are wrongly classified. So in the work, I started from two study areas, which are one to the north, one to the south of each other, the same shape. And I went in I did an initial delineation on LiDAR, and then I went in the field and I identified mounds. And then in the field, I checked if they are really burial mounds or other features. And there are many other features. You see, there are errors from the filtering and interpolation. There are houses, again, which were not filtered. Sometimes landslides, have small mounds which can be associated with burial mounds. Also electric pole bases, and many things. So in my data set, I flagged them. I also, you see the embankments. There are some reservoirs in the study area. You see them here. And there are a lot of errors. So I removed all those areas. I didn't include them in the processing. Okay, these are photos from the field. Usually in northeastern Romania, since the burial mounds are from Bronze Age, they are located on floodplains, small terraces, or plateaus and ridges, and usually they are visible from, from far away. I cannot enter in details what is the archaeology behind this, sorry. But anyway, it's quite interesting, and I think my catalog could be further used by fellow archaeologists to obtain also some landscape archaeology. And after I saw all the papers about the crop marks, I have also in mind, because we also have flattened burial mounds, to later do this also on aerial images, because it will complement the features that are still visible from a topographical point of view. Here you have the delineation. Delineation on shading, it's tricky. Objective delineation on shading, it's tricky. In my approach, I used segments. So basically, I found a geomorphometrical variable, which when I do segmentation, so I start from minimum. There are methodologies in the literature, the watershed segmentation, starting from minimum or maxima values. The method adds pixel to that minima or maxima up until there is a change in the watershed. And when there is a change, it will stop. So basically you obtain regions. In this case, I used a very simple measure of convexity. Okay, it's computed in the vicinity. If all the pixels are higher than the central one, it's a convex feature. It doesn't matter how steep or how gentle it is. It matters that it's convex. And the results, the segmentation results, are quite good in terms of identifying the central part of the burial mound, because I told you, although I search for convex feature, I have concave parts at the base because of the tillage. So you see, it's basically a compound shape. So in my point of view, I want to do the work on the convex shape. So the idea is that I identify the location of a burial mound, and sometimes, or I could devise a new method to also delineate them. But there are discussions about the delineation. In my point of view, if I manage to find a segment which can be flagged as a burial mound, it could help archaeologists to create this type of inventory. So the issue is that there are many mounds from this point of view. So I also devised an algorithm which is identifying pixels which are peaks. All the neighboring pixels are lower than that pixel, so it's a peak. So I need concave segments with a peak. So from, I don't know, 100,000 segments identified, I select only 12, 14,000, which have this kind of peaks. And only for those selected segments, I do the algorithm of classifying based on a training area. And I also have a validation area. So for the training area, I have found 69 burial mounds for this area, and I validated here where I have 29. Unfortunately, two here and two here are burial mounds that have topography, but they are anthropically modified. One is crossed by a road. So geomorphometrically, it will not be necessarily like a mound with a peak, but rather, like a nose, like a shoulder of a hill slope. So it's tricky. So the method fails. The selected peak identification fails for two of them. Then usually for artificial intelligence or machine learning techniques, you need to have big data, a big amount of data. So when I say big amount of data, basically I have computed all the variables, geomorphometric variables that cross my mind. And also I computed shapes indexes. So the segment has a certain shape. I favor shapes which are, let's say, close to a circle. So I also included those. So basically around 700 features, variables I used. I also checked them with these box plots, training, validation, non-burial segments. So you see that usually the burial mound segments are quite different than other convex segments. So there is a clear geomorphometrical signature of these features. And the machine learning techniques, which are non-linear, basically can find some patterns and identify them. First, I used random forest approach. And here you have basically the workflow. We have the DEM, we identify the peaks, then we compute the local convexity, we get the segments, then we keep only the segments which have a peak inside them. And then these are the selected segments. And then we are running the algorithm, and you see only this segment remains as a burial mound, and it is a burial mound. Then I played also with deep learning, multi-layer perceptron. And if here the results were the best in the literature, actually here I got probably overfitting. This is a big issue with machine learning algorithms. They overfit, which is not necessarily a bad thing. It depends on, you want to move them on other areas. This is a big issue. You do your work on a training and testing area, it works, but then you want to translate it on a bigger area. And actually this is what I am going to talk about now. These are very technical stuff. If someone has questions, I can explain. I told you the values are quite good, the classification measures. Usually we want to see the metrics, true positives, true negatives, and so on. The idea is to have a very small number of false positives in order to have basically a small amount of time searching for the segments in the field or in the office which are actually wrongly classified. If you have, I don't know, in a certain area 100 burial mounds and you obtain 500 false positives, it's tricky. Although the accuracy, the overall accuracy looks fine, but actually it's tricky when you want to do it on a bigger area. So my idea was to minimize these things. And I managed to do it especially using objects. In the literature, there are methods on pixels, but with pixels is difficult. You see here, false positives. A lot of pixels areas would have to be checked. In my case, I have segments. It's quite easy in a GIS software to take the attribute table and zoom in, zoom to segment, you check them, and I don't know, in 1 week you can resolve a certain area. While with pixels, it's very tricky. My goal, it's basically to cover this area of northeastern Romania, which has very good LiDAR DM and has many burial mounds. Almost all of them not mapped, not identified. Of course, then I can switch to Dobroja. There is also LiDAR in the western part of the country where we also have burial mounds. We have just limited LiDAR in the southern Romania where there are also burial mounds. Okay, so the idea was to move on these areas, and unfortunately I do not have all the data, but I can show you on a smaller area. So I just have taken the model which was obtained somewhere, and I applied in another area in this big study area. And the results are quite good. I will show you. This is another area. You can clearly see wide floodplains, plateaus, gentle hill slopes, and very steep hill slopes with a lot of landslides. So many, convex features. But with my methodology, in red, you see the segments which are flagged as potential burial mounds. And then the result on a gentle plateau. You see here a burial mound, which has topography, and these smaller ones, are very smoothed, you see, by the tillage. But I was able to flag them. Of course, I have also false positives, but you see, there are very few false positives. And these white ones are those flagged as possible burial mounds. So by applying this methodology, of course, I cannot replicate the 100% accuracy from the training and testing area, but I can basically obtain very good accuracy. And for the future, I wait for some funding to apply also the transfer learning. What is transfer learning? You obtain a model in a certain area, and then you could add to that model some information from other areas, but the information, you do not have to rerun again the model. You just include some, for example, some delineated burial mounds to be included in the model. This would apply, for example, if I go to Dobroja and want to apply there, because those burial mounds could be a little bit different than the ones from northeastern Romania. So there are big opportunities here, but anyway, in my view, with this methodology in northeastern Romania, I can do the job. Of course, I'm waiting for funding in order to implement it, and I also want to do it to be available as a web processing service. So you have some LiDAR data with burial mounds, you upload it on my server, everything is running, and you get the values. So this is the best way to validate and to obtain something that could be used by the community. So thank you very much. If you have questions, I'm here.